All right, everyone. I want to do a quick, super quick video to actually discuss a couple of things before we actually take this idea of conservation of power and actually start utilizing that to basically make our system more efficient. So two things I want to make sure that we understand in terms of definitions. Number one, apparent power. Apparent power is literally nothing more than the magnitude of the complex power. So in this case, if we had S is equal to 100 at an angle of 15 degrees, then the magnitude of basically that complex power, which is the apparent power, is actually nothing more than just 100 volt amperes. If we look at this though, in terms of the real power and also the apparent power within the system, we got 96.59 watts plus J 25.88. But the apparent power is nothing more than the magnitude of the polar form of the complex power. Now, I've said this phrase in another video, and I want to make sure I come back and discuss it a little bit. But power factor, and what really is power factor? And for us, power factor really helps kind of give us an idea of what type of system that we're actually looking at and its efficiency. So by base definition, a power factor is really more of the real power that's actually being supplied within the system divided by its actual apparent power. So in this case, guys, if we look at the real power over that apparent power, then the ratio of the two basically says that the real power to the apparent power, in this case would have been 96.59 watts, divided by 100 volt amperes, actually gives us basically a percentage, or in this case a decimal value of 0.966, but that essentially says that we have a 96%, well, roughly 96.6% percent efficiency within our system, where 96% of that power that's being supplied is actually real power that's actually being absorbed. So, also another way we can think about that in terms of calculation is cosine of the phase angle of basically our complex power. So cosine of 15 degrees actually comes out and gives us the exact same value, so 0.966. So there's two ways that we can actually look in terms of the power factor. The thing is that a lot of the times, only thing that we need within the system is a little bit of information, and we actually have basically everything that we need to know about the system. Sometimes when we actually have maybe say just the real power or the reactive power or maybe even the apparent power, when we have the power factor, we actually can denote everything else within the system because the phase angle of that complex power is nothing more than the inverse cosine of the power factor itself, of that efficiency. Now, one thing I didn't actually write on here, and I'm going to note, is that we also can know what type of reactive power we actually have by saying whether that power or the power factor itself is actually leading or lagging. And from other discussions that we've had, 0.966 lagging means that we have an inductive system, mostly inductive system. It doesn't mean that we don't have capacitors within the system, but mostly inductive. If I say leading, then that means we have negative reactive power, which is basically meaning that the system is capacitive. But here, positive reactive power, that is exactly what we expect for an inductive system. But if we had negative reactive power, the power factor would actually be leading. We always have to say whether that power factor is leading or lagging so that we actually understand what type of system we have. If it's mostly inductive in nature or if it's mostly capacitive in nature. But the thing is that if we have a system that's not efficient, then we can actually consider basically the power factor in terms of maybe how we can actually essentially start correcting that system, whether it needs to be corrected. And also to give us a visual in terms of not only the power factor and the efficiency, but also the apparent power to the real power as well as our reactive power is what we call the power triangle. So as we've already seen, we've been working off a real and imaginary axis all up until this point. And so if we consider the real power being on the real axis, then we get 96.59 degrees, watts. But of course, if we actually essentially kind of similar to vector arithmetic, if we go up the imaginary axis by 25.88 var, then the hypotenuse between those two is actually going to be essentially our apparent power, 100 volt amperes, and basically the phase angle that we actually get is 15 degrees in between the two. So just a couple of concepts I wanted to actually look through, essentially the apparent power, our power factor, and then also the power triangle, because when we come back with a video that we're going to talk about this concept of power factor correction or increasing the efficiency within our system, we're going to be using all three of these terms. So here we're actually going to be taking maybe this Q here and we're going to drop that. But how we're going to drop it is going to go right back to the law of conservation of power. And we're going to be able to determine exactly what type of maybe capacitive value we want to add into the circuit that's actually going to increase our efficiency within the system, or basically cause this power factor here to go more towards 100% efficiency. So we're going to come back and we're going to look at that till the next time.